here, except we've written it upside down. Because if you were to label the oxygens with oxygen 17 or O18 label, then indeed you could tell the difference. But otherwise you can't, once you're here. And so now we have an excellent leaving group. This one pulls like hell on this carbonyl carbon. Now chloride can come in this place. In the case of alcohols, where this was an R group, chloride or bromide would come in and do an SN2 with this leaving and self-destructing. And I'll remind you how it does that in a second. Here we have to go through additional elimination. So here it is. Here's our leaving group. It pulls like crazy. We are working under acidic conditions, so this gets activated by protonation, and then you get the protonated species. Then chloride comes in as the nucleophile addition. This is our tetrahedral intermediate, and then proton comes off. The electron pair comes in. You're kicking out the leaving group. And notice that when the leaving group leaves, it doesn't make chloro SO2 minus. That species, as this electron pair goes in here, actually falls apart. Chloride now realizes it can take off as chloride anion. Often groups like that are often called suicide groups because they self-destruct on leaving. Okay? And this is great. There's a great driving force for this because entropically you're making several molecules out of one. And you're also making just pure gases, HCl and SO2, which blow out of the reaction mixture. And this is how you make acyl halides, acyl chlorides or acyl bromides. And so now you can hook this into Friedel-Crafts acylation chemistry, where we used acyl halides. Now you know how to make acyl halides, namely from carboxylic acids with the reagents that I've shown you. And we know how to make carboxylic acids from smaller pieces, So this expands your Friedel-Crafts chemistry tremendously, such that you can build up now a rather large acyl benzene from smaller fragments using this kind of chemistry. Okay, so PCl5 does the same thing. It turns a carboxylic acid into the acyl chloride. And PBr3 is used for the bromination. Acyl bromides are more reactive, more corrosive than acyl halides. HBr is a stronger acid, and so you use PBr3 to make these guys. Okay, so much for acyl halides. So what about the next class of carboxylic acid derivatives, anhydrides? So notice that what we're now doing is we're going from the halogens as the substituents to the acyl group, the most electron withdrawing groups, one to the left, oxygen. Oxygen is less electronegative, so those acyl functions are less reactive. This is a special oxygen. It's not an OH oxygen or OR oxygen as in esters. It's an acyl oxygen. And so I'm focusing arbitrarily, by the way, since this is symmetrical, on the right as being the X group and the left being the acyl. Of course, you could go do it the other way around, and this would be significant if the anhydride were unsymmetrical, and this is one of the reasons why you use symmetrical anhydride, so you don't have that complication. So this oxygen pulls more than the oxygen of an OR, of an alkoxy, because the carbonyl pulls extra. Okay? So it's a hotter than usual oxygen, but it's less reactive than the halides to the right of it. Okay? That's how they fit in. So how do we make these? There are two ways of doing this. One is the low temperature, high yield, very effective way that one uses in synthetic chemistry. Namely, you take an acyl halide and react it with a carboxylic acid. So now you're combining a very reactive carbonyl function with the less reactive carboxylic acid function. And the mechanism of this is, again, as usual, the electrophile attacks on the carbonyl oxygen, or the carbonyl oxygen is the nucleophile that adds. You do addition, elimination, chloride kicks out comes the anhydride. Quite straightforward. This is high yield. Now, anhydrides are called anhydrides because formally they are formed from two carboxylic acids minus water, kicking out water. And in principle, one can do this by just blasting the living daylight out of them. And indeed, this is done industrially, for example, in dicarboxylic acids. At 300 degrees, they blow out water. And here again, the mechanism is this oxygen attacking as a nucleophile, addition, elimination, and you get the corresponding anhydride. What is that? Is the chancellor trying to reach us? It sounds like a phone. Oh, it's a phone here. Oh, the water bottle? Ah, here, right. I don't even know how to work this guy. Ah, it's a phone sex line. Do you know how to turn it up?
You have to call this line now. It's in a phone call.
Yeah, this phone is in Pimentel. It goes left there. Okay, come back, pick it up. Sorry, my entire family has iPhones, but I have the cheapest cell phone imaginable. It's one step up from a pigeon, and I like it because nobody has my number anyway because I don't want to be reached. Okay, so if you blast this at 300 degrees, it blows up water. So this is not the way to do your chemistry, the chemistry I'd like you to do when you build up molecules. This is way too destructive. Okay, so what about esters? Esters now are a very prevalent class of molecules in nature. Esters frequently have very nice flavor. There are many herbs, flavors of fruits. They're all esters, banana, apples, and so on. And these can be made indeed from the component pieces, namely a carboxylic acid with an alcohol. What you need is a pinch of sulfuric acid. You mix the two, you add literally a drop of concentrated sulfuric acid, and you set up an equilibrium between the starting materials and the products, which is the ester and water. Notice what we're doing is we're exchanging OH for RO. This is kind of reminiscent of an alcohol with acid reacting with another alcohol to make an ether, okay? Except that we're doing this on the hydroxy function of the carboxylic acid. Notice also when you look at bonds broken, this COH bond, you're making a COR bond, that is essentially the same, and you're breaking an OH bond and you're making an OH bond, that's the same, slight variation because of the substituents. The delta H is essentially zero. If you're taking two molecules and making two molecules, the delta S is very close to 0, meaning that the delta G is very close to 0, meaning that this equilibrium is 1-to-1. So we are back to a classic equilibrium situation of the type we have encountered the last couple of weeks. An equilibrium that can be driven by using the excess of any one of the starting materials. So if your carboxylic acid is the expensive part and you want to turn it into an ester, use a cheap alcohol, methanol or ethanol, as a solvent, and that drives us to the right. If the alcohol is the expensive part, then you use a cheap acid like acetic acid to make the ester and use excess of it. That drives it to the right. The fact that this is so readily reversible also means that you can shift the equilibrium from right to left. So if you wanted to hydrolyze an ester, you can do this in the presence of acid catalysis, excess water, and you now go from right to left. Very reminiscent of acetal formation, for example, where to drive it to the right, you use excess alcohol with acid. To drive it to hydrolyze an acetal, you use excess water to go back in the other direction. So here's an example of the simplest one, acetic acid, or almost simplest. Acetic acid and methanol using that as a solvent goes 85%. That's a literature reaction, actually. Somebody did that to check, to just compare yields. And that's straightforward. So there's a mechanism. That mechanism I'm going to do on the board, because it's one of the classic mechanisms of carbonyl chemistry, and it shows up in one form or another in almost all exams. So let's do it for the acetic acid plus methanol. Everything is reversible. Methanol is not a strong enough nucleophile to attack the relatively unreactive carbonyl of a carboxylic acid, so we improve the electrophilicity of this carbon by protonation. Now this carbon is a much better electrophile. Now it gets trapped by methanol. And this guy loses proton to make the so-called tetrahedral intermediate, which is nothing else but the methanol adduct to the carbonyl function. Okay? If this weren't OH but were R, this would be the hemiacetal. Right? It's completely identical. The only difference is now we have an extra OH. And that extra OH can now leave, and we make that leave by protonation, classic activation of OH to turn it into a better leaving group. And indeed, it leaves, and I'm kicking in the electron pair. Notice that this extra kick is not necessary. You don't have to do it. It's arbitrary. It gives you two different resonance forms of the same molecule. So I'm just kicking it in for the fun of it, because this is now the protonated carbonyl, and you can clearly see how this then gives the product. So we're losing proton in the last step, and that gives the final ester. And of course, ester hydrolysis with acid is the microscopic reverse of that. You protonate here, gives you that activates the carbonyl. Water adds to here, gives you that. Yeah, it just go back. It's basically a relay mechanism where you exchange OH for OR. Something we've done plenty of times. The last time we did this was turning a hemiacetal into an acetal, where we exchanged OH for OR in the presence of acid. And there is a movie on that. So here we go, protonation to activate the carbonyl. Notice there's the other resonance form, which is the carbocation resonance form. Gets trapped by alcohol, and then loss of the proton. And that's the methanol adduct to the carbonyl function, acid catalyzed. And now we're making an OH leave. It's arbitrary which one you pick, by the way. I picked that one, and the movie picks that one. And better leaving group, you take off, and then... so here's the carbocation, which I didn't write. I wrote straight the other resonance structure, which is the protonated carbonyl. And there you go. Now, we said that with acid we can hydrolyze. So that's the reverse of the ester formation written here, acid and excess water. So the equilibrium is now shifted to the left in that sense. For esters, we can also hydrolyze with base. Remember, we can't make esters with base because the base will deprotonate the carboxylic acid and take it out of the picture. So that's no good. But the reverse can be done with base. And that's straightforward addition, elimination, such that if you have an ester like this, hydroxide will add, electron pair goes out, comes back in, kicks out alkoxide, and that gives the carboxylic acid and the alcohol. And this slide here is actually material stolen from chapter 8, where we discussed how to turn Rx into ROH. And remember, the simplest way was SN2 by hydroxide, but it had big problems because as soon as you're branched, alpha or beta branched, sterically hindered, OH will eliminate rather than substitute. Okay? And so the way around that was to use a softer form of OH, of O-, namely carboxylate. Carboxylate, the negative charge is delocalized over the carboxyl function. So it's much less basic, but it's still nucleophilic. And that can do an SN2. And so the example we chose there was a beta-branched system where sodium hydroxide gives you a lot of trouble with elimination. Sodium acetate does the SN2, 95%, very clean. And at the ester stage now, you can hydrolyze. And you can hydrolyze either with acid or with base. And at the time we did it with base, additional elimination liberated the alcohol. So in this particular ester, it was the alcohol that was the valuable part because it was part of a discussion of turning Rx into ROH. So it's straightforward additional elimination. Now again, there is an intramolecular version. Alcohol plus carboxylic acids. You can have a hydroxycarboxylic acid, and that can be induced to cyclize. And cyclic esters have a common name called lactones, okay? But you can just call them cyclic esters. Basically, same mechanism. The only difference energetically is that it's an intramolecular reaction, which has already intrinsically an entropic advantage. But there's also the entropy of the reaction is much better because one molecule turns into two, the lactone and water, which means you're increasing this order, and that's favorable. Okay? Delta S is positive. Okay? And since the delta S term in the delta G term has a minus in front of it, it makes a negative contribution to the delta G. And remember, the more negative the delta G, the better for the reaction. So that means that it's not a one-to-one mixture anymore, as we saw for acetic acid plus methanol. 1-to-1 equivalent gives you 1-to-1 mixture of the components. But rather, it's now 10-to-9. Okay, so the entropy pushes this into this regime here. That's irrelevant for your synthetic chemistry, but it's an interesting aside. All right, let's have a break.
I have a question about Michael addition.
Yeah. Sorry, I didn't get back to you.
It's fine.
We turn carboxylic acids into the acid chlorides and bromides. Halogens, strongest polars, those are the strongest, the most reactive carboxylic acid derivatives. This will become significant because they're great to substitute with all the other nucleophiles that we've discussed. Slightly less reactive are the anhydrides, where instead of halide we have carboxylate as a leaving group. Quite a bit less reactive are the esters, where we have alkoxy. And then, if we move from oxygen to nitrogen, we have an even less electron pulling atom. So they're the least reactive. And we'll discuss this in greater detail in the next chapter. But